tree. So I did
All right,
a
let's
tree
get
sort.
this going. Welcome everybody, thank you for coming out. My name is Jeremy Schneider. I am one of the organizers here. Lloyd Albin, also an organizer. Lloyd has been running this group for a very, very long time, since longer than I've been here. And also been using Postgres for a very long time. So if you have Postgres questions, well, lots of people here can chat. I'm going to run through some quick announcements and then we'll get going because you didn't come here to listen to me. Bathrooms, just so everybody knows, there's a hallway just out behind that wall. There's bathrooms, I think, just to the right around that corner, and there's also some down there. Let's see. I think everybody got name tags. Thank you very much. There was a sign-in sheet. Please do put your name on there. That kind of helps us. You'll notice there's no email address. That's mostly so we know how many people came, how much pizza we need to buy next time, stuff like that. So I do appreciate having the sign-in sheets. If you want to get notifications, the way you do that is you go to meetup.com. That's the best place to get notifications. So if you're not already signed up on meetup.com, that's the place to go for actually finding out about future meetups. Three more quick things. There's a library. Our user group library is that just big pile of books sitting on the shelf over there, and you're welcome to borrow books. There's a little clipboard with a piece of paper. If you want to borrow a book, go ahead and just take it. I do ask that if you borrow a book that you put down some actual contact information, so if it doesn't come back in like a year or so, I can just reach out and ask how great the book is. And I'll warn you, if you keep it for a long time, I might ask you to come back and give a book report. Tell us the best parts. So that's the library. Next to the library, there's a little sheet of paper called the Happiness Hints. I like to just give a quick plug for those. I didn't come up with those. That's mostly stuff that I've just kind of collected and heard from other people over the years, but it's kind of a set of best practices type of things related to Postgres specifically. Like I said, not original ideas, but kind of just some stuff that's been collected, so you're welcome. There's 2 left. Maybe snap a photo if somebody can get one and snap a photo after that, and then whoever is the last one will take the other one if you want. I'll print some more. So that's all of my big announcements. Oh, and then the other thing is upcoming meetups. So we always for a couple of years now, we've taken a break for the summer, just lots of things going on. So what happens is next month on July 3rd, which is the first Thursday of July, we are going to come back here to this building, but we're not going to have a speaker. This is a traditional thing that Lloyd's been doing for ages, that every year in July, we do a barbecue, a cookout on the back porch by Lake Union. It's real gorgeous. It's a lot of fun. Lloyd will bring this. Do you want to actually just kind of announce this?
I bring hamburgers, beef burgers, I bring turkey burgers, and I bring veggie burgers, and I bring hot dogs. And everybody else is welcome to bring additional food. And we hold the barbecue upstairs. There's a gas grill up there, tables, everything outside. If the weather turns bad, we have a room immediately inside that we can go into and actually eat in there. But otherwise, it's up on the 5th floor of this building, right overlooking Lake Union. It's got a great view from there.
It's a lot of fun.
And yeah, I started this because July was the lowest attended month of the year for SEAPUG. And so I said, well, hey, why give a presentation? Let's make it a social event. So this is our social event of the year, where we get together and we don't present, we actually just come and chat with each other, and spouses are welcome. Yep. So yes.
Yep, so that's next month, and then after...
This is very fun.
Eric attests, it's very fun, yes. So after that, we'll take a break for August, and then we'll come back in September. We'll start kind of our fall series of September, October, November, December meetups, which I'm working on now. So actually, another thing is, if any of you have a topic you'd like to talk about that is related in some way to Postgres, I'd love to put some folks on the schedule for the fall. So yeah, please. I'm really serious about that. It's a fair bit of work to find speakers. I spend a lot more time than you think trying to sort of figure out the schedule and like looking for people. So,
and it's good prep for additional conferences that you may wish to speak at later. We will be holding a Postgres conference in Seattle this fall. So if you want to give your talk here first in preparation to actually give it at a larger conference, and then PASS is held in Seattle, and it also has Postgres tracks running at it. that you could give a presentation at also.
Yep. All right. So any other, Lloyd, anything else announcement-wise? All right.
I'm good.
Okay. So on that note, let me introduce our speaker for tonight. Noah, thank you for coming up from. Are you from the Portland? Now I've forgotten. Were you in the? You weren't in the Portland area, or were
I am. So I'm from Vancouver, Washington, just outside Portland.
Let me real quickly just read. Noah is a software engineer at EnterpriseDB, where he helps build Postgres extensions to support AI workloads. He has a passion for developer experience, from improving internal tools at Salesforce to managing bookstore inventory systems. Sounds like there's a story there. To implementing automations at a healthcare tech startup. All kinds of fun stories here. Noah brings to us a deep appreciation for systems thinking and developer experience to his work in Rust and Postgres. Outside of work, you'll find him exploring the Pacific Northwest, working on embedded electronics and practicing finger guitar. So everybody give a quick round. Welcome.
We currently don't have sponsorship, but EnterpriseDB was our first sponsor and used to buy our visas years ago.
There you go. I cannot claim responsibility for that, but. Oh, a spotlight and everything. All right. Okay. Here we go. Well, hello, everyone. Is it better if I use the microphone? Is it? OK, it's large enough. I'll try to stay up here. Well, thanks for having me here tonight. I'm excited to share a little bit about my journey using Rust and Postgres for AI workloads. And basically, this is kind of an excuse to talk about my Rust side projects and how my personal curiosity led me to the Postgres AI work that I am contributing to now. I'll cover a little bit about how Rust fits into the Postgres ecosystem, basically what I'm building at work, and some of the lessons that I've learned along the way. This talk is meant to be technical but practical. So whether you're a Postgres user, just kind of a Rust fan, or someone exploring the foundations of AI, I hope you find something kind of useful or interesting. This is not a full Rust tutorial. I am not teaching you all of Rust tonight, but hopefully this is still something that's interesting and kind of gives you a glimpse behind the curtain. I can kind of breeze through this. You guys already know my name's Noah Baculi. I'm based in Vancouver, Washington, just outside Portland, Oregon. And yeah, I work for a company called EnterpriseDB, and we're a company that provides tailored Postgres solutions and support to large organizations. My background actually started in mechanical engineering, but along the way I found myself increasingly drawn to writing code, first for internal tools at Salesforce, and then in the healthcare kind of tech space, and now at EDB. Throughout all of my projects, like Jeremy mentioned, I found myself continuously drawn to the aspects of developer experience. So many of my opinions are kind of guided by that lens. Before we dive into the Postgres and the Rust side, I want to take a step back and talk about kind of the basics of the AI workloads for those who might not be super familiar. Oops. There's a lot of hype about AI, especially in the last few years, and it's a very rapidly changing space. Basically, what are people using AI for? Understanding these core workloads helps us reason about where the AI should run, how to make it efficient, and what role Postgres has to play in that. There's been a lot of buzz about apps like ChatGPT and Claude. I heard a lot of discussions there. And a lot of those real-world workloads are actually more behind the scenes and have actually been improving our lives for longer than some of the hype has been around. The first category of workloads are what I think of and call model operations. These are basically the lower level primitives that have somewhat limited applicability on their own, but they unlock much more functionality when they're combined together. That's things like embeddings, classification, and re-ranking. I'll talk about embeddings a bit more on the next slide. But classification applications are basically different kinds of scoring. You might want sentiment analysis for some kind of user-generated content or categorization of documents. Another example is filtering of transaction events. And that's a big focus for a lot of our customers, especially, you might imagine, the financial customers. As an example of model operations, if we have existing data on product reviews, we can calculate the embeddings to capture the semantic meaning of those reviews. Then we can classify each one of those for sentiment, whether that's positive, negative, or neutral, and then re-rank those reviews based on the author's influence or kind of the helpfulness of the review. And then that way we can surface the top reviews to the users automatically at query time, kind of right inside the database. At least that's the dream. Another AI workload is vector search. And this is one of the most foundational AI workloads. At a high level, vector search involves comparing high-dimensional vectors. These, what we call embeddings, represent the semantic meaning of data like text or images or audio. Basically, when two embeddings are close together in vector space, it means that their source data is semantically similar. The most common application is semantic search. So instead of relying on keyword matches, we can find results that are conceptually similar to a query, even if the wording is different. Vector search also powers recommendation systems, like suggesting similar movies, think like your Netflix, similar songs, think like Spotify, or even like similar products based on a user's past behavior, think like an Amazon, right? Vector search is also used in deduplication and in clustering, where we group similar items together for analytics or some kind of downstream operation. In the example for vector search, we can, again, calculate embeddings from product descriptions and then use vector search to search for similar products with semantically similar descriptions, even if they might not have the exact same keywords. The last AI workload that I want to talk about as kind of background is retrieval augmented generation, or RAG. And this is a technique that enhances large language models by combining them with a retrieval system. So rather than asking an LLM like ChatGPT to generate answers just from its training data, RAG augments its inputs by pulling in relevant, up-to-date, or proprietary information from an external source, which could be a Postgres instance. This is especially useful in domains like customer support or internal tools, where we really value the accuracy and the relevance, especially if it depends on company-specific or time-sensitive data. So in this example, if a user asks, what is our company's refund policy in France, that might not be something that ChatGPT would know off the cuff. And with RAG, we can supplement LLM with that policy text data straight from the database in order to generate a more tailored, context-aware answer. What we're seeing is that more and more teams want to run AI operations closer to the data for a few big reasons. The first is faster iteration. We all know that AI is a rapidly evolving space that's changing all the time. Reducing the ETL means that you're not constantly exporting, transforming, and reloading the data just to try things out. Second, this makes it a bit more easy to scale to large data sets because, again, you're not moving them around. And then similarly, the latency goes down, especially for use cases like search or recommendation, where you really care about that snappiness. And then finally, keeping everything in Postgres gives you more centralized governance for access control and auditing, that kind of stuff. So this is where pgvector comes in. This is a Postgres extension that really gave us a fantastic foundation for vector search inside of Postgres. And that's great, and it really showed the demand for this kind of work. But pgvector, we found, had some limitations, especially around like index support, as well as some of the supporting infrastructure that a lot of workflows need outside of just the embeddings. These kind of supporting infrastructure workflows most often have to happen outside of the database, right, via like ETL. So that's where the company that I work for started looking for other options, eventually leading them on the journey to build their own AI extension. When we first started exploring what an AI extension for Postgres could look like, we chose to prototype in Python. The first reason was it was just a familiar language for our team at the time. We were a small team back then. This let us move more quickly without a big ramp-up period. We also weren't sure how long-term this endeavor was going to be. And not only that, the Python AI ecosystem is incredibly rich. There's a reason that so much ETL leverages Python, right? This enabled this enabled us to build early features fast and focus on exploring the problem space rather than the core kind of infrastructure. This was our tech preview. It wasn't necessarily something that we expected to ship in production, but rather a way to test ideas out quickly. And we were able to experiment with different user experiences and try out different APIs, for things like embedding and classification, and really get feedback from different users. But while the developer experience was solid and it was a good fit for our tech preview, there were some cracks that started to show. The first big one was trust and isolation. So in Postgres, PL Python is actually considered what's called an untrusted language, which means there's no sandboxing, so you can't really run it safely in a shared environment. We also started to see issues with performance. Python just unfortunately isn't really suitable for the kind of production scales and speed that we required. Especially for compute-heavy operations like embedding or classification, it quickly became a bottleneck for us. We also ran into Python's global interpreter lock, or GIL. This caused problems for us in high-load or distributed environments, which are pretty common for us, especially when multiple users are running model operations concurrently. So while Python was a great tool for discovery, it just didn't really hold up under the real-world production constraints that we had. And so that's what pushed us to explore some alternatives. C has long been the standard for writing Postgres extensions, and for pretty good reason. It offers maximum performance, tight integration with Postgres internals, and full control over memory and execution. It's also, of course, a trusted language. I would hope it is, which makes it safe for production use with those standard permissions. But that power does come with trade-offs. Writing in C means a steeper learning curve for some of our engineers, slower development, and higher risk of bugs like seg faults and memory leaks. When it comes to AI machine learning, C didn't seem like the best fit. Most of the modern tooling is built for higher level languages, so integrating models or handling things like vector similarity or tokenization seemed like it would be a bit harder. C is great when you need to squeeze out every little bit of performance, but we didn't find it to be the best fit for our fast-moving AI extension development. SQL is also a natural starting point for Postgres developers. Of course, it's native to the database, has no extra dependencies, and it really excels at data filtering, aggregation, and preprocessing. That's why we use it. It also plays well with Postgres features like indexes, views, permissions, so it's easy to audit and debug. But as you might imagine, we hit our limits with SQL very fast when we tried to use it for AI. It's just not really expressive enough for that kind of complex logic, and it lacks native support for model inference, embeddings, and any of those kind of external tools. Performance can also be tricky with row-wise operations, and there's not really strong developer tooling or type safety to speak of. So while SQL is great for prep and orchestration, it's not really ideal for implementing these kinds of like core AI logic. So Rust gave us a great balance of performance and safety. It's close to C in performance, but with strong type checks and memory guarantees that help us avoid some of those most common bugs. This performance helps minimize overhead for the underlying Postgres instance, which is obviously important. Rust supports concurrency without a global interpreter lock, making it suitable for scalable AI workloads. Specifically, the pgrx framework, which made building Postgres extensions productive and safe, and the Rust AI and machine learning ecosystem is steadily growing, even if it's not as mature and may not ever be as mature as Python's. However, there are trade-offs, as there always are. Compile times are longer, and the learning curve can be pretty steep. You have to be careful with FFI and the unsafe code, especially when you're bridging to C libraries or Postgres internals. Still, the combination of speed, safety, and maintainability made Rust a really solid choice for us. And we'll dive into each of these a bit more later. So these are all the trade-offs that EDB was considering as they looked to expand their team working on the AI extension. Other teams at EDB had already been successful building with Rust, so they were interested in candidates with Rust experience. So I want to talk a little bit about how I came to be one of those candidates. So before I started learning Rust, Python was my main language. It got me pretty far. I used it for automations, data processing, and even some early machine learning projects. But as the scope and complexity of my work and my projects grew, I definitely started to feel some of its limitations. Really, it was just kind of my personal curiosity. I wanted to go deeper. I wanted to understand how things worked at like a systems level, and basically to write statically typed software that was both fast, reliable, and free from many of the runtime exceptions that I was just kind of fed up with Python. I also wanted one language that could span multiple domains, something that I could use for my very diverse set of projects. At the same time, I was looking for a language that would challenge how I thought about code. Basically, I wanted something that was different enough from Python to be lerth and interesting to learn. So for me, Rust checked all those boxes. It offered the strong safety guarantees, great performance, and a modern approach to software design. And it just kind of made sense to me. It seemed interesting, and I thought I'd give it a try. When I started learning Rust, I approached it the same way that I've learned most technologies. And that's basically just by building small projects that I found useful or fun. One of my favorite early projects was a bot for Space Traders. Space Traders is a programmable API-based space trading game made specifically for developers. And I definitely recommend it if anyone somehow doesn't get enough coding at work. I know we've all had some of those periods sometimes. You get a little too hung up in the trainings or something like that. It's definitely super in the weeds, but it's a lot of fun. And for me, it was a fun challenge to let me play with the optimization strategies and async Rust and help me get used to things and thinking of things in terms of futures and tasks. But one of the early hurdles that I ran into was error handling. Rust doesn't have exceptions. Instead, every operation that might fail returns what's called a result. And you have to explicitly handle those failures. Whether it's a network request or parsing a response, you have to think through what could go wrong and decide what to do when it does. At first, that felt tedious. But over time, I saw the benefits. It really makes the sources of failure visible, and the compiler helps you track down how those errors flow through your code. And it actually made debugging for me a lot easier, because I wasn't chasing down silent failures that just came up from a stack trace somewhere. These small projects gave me a solid foundation in the language and its mindset, and that paid off when I started using Rust more seriously at work. So here's a basic example of a function in Rust that can fail. The isEven function takes an integer and returns a Boolean. Because of the type system, this function just cannot fail. And that's visible from the function signature. Of course, Rust can't guarantee that your logic is correct, but this kind of code is straightforward and predictable, so functions like this are easy to test and to reason about. And in Rust, they're also very efficient. With minimal overhead. By contrast, let's say we try to write a function that parses a string into an integer. In many languages, you just return the happy path value and let exceptions handle the failure case somewhere else. But in Rust, there are no exceptions. Every fallible operation must be accounted for. So if we write this function and forget to handle the possible error from parse, the function that we're using inside, the compiler immediately lets us know. Here, it tells us exactly what's wrong. We said the function returns an I32, but the function that we're using, parse, actually returns a result, again, because it can fail. This mismatch is at the core of the error, and the compiler highlights the exact line and the expected type, making it much easier to understand and fix the issue. If you've written any Python recently, you might recognize this kind of error. This is pretty recent. And I'm glad that Python is adapting more explicit errors and pointing you to exactly where they are and everything. I very much approve from a developer experience perspective. Let's see. Similarly, in this function, we read from a file which might not exist and parse its content as a number, which might not work. Each of these operations, again, returns a result, like we saw on the last slide. But this time, we have something called the question mark operator, and that propagates the error upwards if something goes wrong. But again, that's something that we have to explicitly opt into. In the main function, we match on the result and handle both the success and the failure cases explicitly. And again, at first, this feels very tedious. But it really helped me track down kind of what can fail and what can't fail, especially when failures are catastrophic. At work, I started working in healthcare tech, and we needed a tool to quickly scan directories and find files that closely match a reference file. And this felt like a great case to try to use Rust at work. So I built a CLI, and I called it Busca to look for something. I also wrapped it in Python bindings, so my teammates could use it in their existing automation scripts. And that gave me my first hands-on experience with Rust's FFI story, which turned out to be surprisingly smooth, thanks to some of the great tools in the ecosystem. For me, this project really highlighted Rust's strengths in production, specifically for algorithms. The performance was excellent without a runtime or a garbage collector, and the safety guarantees meant that I could catch many more bugs early with the help of the compiler. And most of all, the language was expressive. Things like pattern matching and iterators helped me write clean, efficient code that was easy to follow the state of. Here's another project, and this one's one of my favorites. And this was basically rewriting a long-running music tool that I've kind of revisited every few years, basically. And what it is a fingerstyle tab generator for guitar. I built earlier versions in Java and TypeScript, but Rust gave it new life. I reworked the pathfinding algorithm to make it faster and more accurate, and then compiled it to WebAssembly for a web demo. And I think this is another great showcase of Rust's performance and portability, too. What really made Rust shine here was the type system. And so that's what I'll talk about using this side project. So enums and pattern matching make it really easy to model musical events and finger positions. I use structs with named fields to help keep things really readable and kind of self-documenting. This kind of strong typing helps catch logic bugs early, especially when you're tweaking things like the scoring logic. So this is an example of how I modeled the fingerstyle tab problem space or domain. And so using these Rust custom types, instead of just passing around plain numbers, I used like a string number new type. It's basically just a wrapper around a U8, but it gives extra meaning to the value. It's not just a regular U8, it's a guitar string. And in the constructor, I can validate that it's within a certain range, do kind of extra logic. But not only that, when I use that type in other functions, I can't misuse it or misunderstand what type a variable is. The pitch fingering struct ties everything together, which fret, which string, and what pitch it produces. And then the pitch enum gives me a type-safe list of valid notes. And I can pattern match on that. I can implement traits to compare the distance between those pitches. Basically, by modeling my application's possible states with the type system itself, the Rust compiler is able to help me adhere to that contract when implementing all of the pathfinding, optimization, and other logic. I actually have a demo or something to pass around for this one. But my embedded projects combine both my mechanical and my software engineering backgrounds. Recently, I've been writing firmware in Rust using Embassy, basically to do kind of async sensor and motor control. And of course, I can do like custom printed circuit boards and 3D printed enclosures. That's not Rust specific. It's just the combination of all the things and why I like it. And I think Rust really fits well here because it gives you high-level expressiveness with that low-level control. Again, there's no garbage collector. The memory is predictable, and compile time checks help catch bugs early, making it very well suited for resource-constrained environments. Because there's a lot of variability in the chips out there and the dev boards, Rust has traits and generics, which make drivers much more reusable. And then static dispatch keeps things pretty quick. It's been great to build safe, kind of real-time systems without sacrificing performance and maintainability. So this is an example of Rust running on bare metal, no OS, no heap, just straight-up code. I actually have this code running on a little dev board that I brought with me. Kind of fun fact, the chip draws so little power that the battery bank will actually cut off power to it after 30 seconds. So you might need to unplug and plug it back in. But I'm going to go ahead and pass this around. It's just an LED blinking, but it's blinking with this code, so I think it's cool. And again, you might have to unplug and replug it in because it draws so little power. So we won't go through the whole thing, but basically the async executor, the GPIO, the timer abstractions, all of those compile down to minimal instructions with 0 overhead. For example, this timer after millis uses a hardware timer. There's no polling or blocking. This is possible because Rust type system ensures safety at compile time, not at runtime. You can't misuse a pin without configuring it properly. And thanks to traits and generics, abstractions like output work across chips without a runtime cost. So this code would work on a lot of different chips. Again, this is high-level code that reads like a desktop app, but it compiles into minimal and efficient instructions suitable for resource-constrained systems like that postcard or that postage stamp. I just think it's so cool that I can write Rust, that I can use Rust to write applications for the large distributed servers that I do at work, all the way down to that tiny little, inch-by-inch square. Speaking of, how can Rust be used to build for the Postgres ecosystem? So pgrx is the core framework that allows us to write Postgres extensions in Rust. It supports PG versions 13 through 18, and it gives us a really ergonomic way to build new database features safely and efficiently. It comes with its own cargo pgrx tooling, which takes care of compiling and testing, again, against multiple Postgres versions, which is really cool. And one of the big strengths is how it automatically maps Rust types to Postgres. So Rust structs, enums, and even the option and result types that we looked at earlier, those get translated to types that Postgres can understand. And it does so while generating the schema automatically. You can, of course, create user-defined functions, trigger functions, and even work with the server programming interface, or SPI, to run SQL from within Rust. And of course, an important safety feature, if your Rust code ever does panic, pgrx will catch that and raise a Postgres error and abort the transaction instead of the entire process, which is a real a feature that was very attractive for us.
Is it trusted language or untrusted?
This is trusted. Yeah, that was one of our requirements. So we'll look at a few examples here. Here's a very simple example of what a pgrx function looks like. The Rust function substring takes a string into integers, just returns a slice of the original string, pretty straightforward. The interesting part is this pgextern attribute that tells pgrx to expose this function to Postgres. It automatically generates the corresponding SQL signature down here. And what I want us to pay attention to is how the Rust native types, the string and the i32, automatically map cleanly to the Postgres types like text and integer. Also, under the hood, pgrx handles things like memory safety, UTF-8 encoding, and even bounds checking to avoid panics. The student of you might have realized that there's a language C here. This is just legacy syntax. It tells Postgres that this is a compiled function from a shared library. But behind the scenes, it really is the Rust code that gets built into that library. Here's another example, this time for a Rust enum that gets mapped to a Postgres enum. In pgrx, we define a rating enum and annotate it with the derived Postgres enum there on the top. On the Postgres side, we see that this gets generated as just a typical create type statement to define the enum. Again, pgrx handles the mapping automatically, so we can use this rating type in our SQL functions and queries just like any built-in type. This keeps the type safety and the business logic in one place while exposing it cleanly to SQL. Yeah?
The names are different. I mean, capitalization, does that happen automatically?
That does happen automatically. That's one of the rough edges we see right now. Okay. They always get converted to lowercase. Yeah.
So am I correct to assume that if you create some additional function Rust, you can actually still consume them into a PGSQL code.
Yeah, yeah. As long as they're exposed. Of course, you can still have like purely like Rust functions that are only consumed by other Rust functions. Yeah.
Well, it's just kind of a follow-up with what this gentleman was asking here to my right. So you're writing this one function on the left in Rust, pgrx,
Yeah.
and then it's generating the SQL function?
Yeah, exactly.
Oh, okay.
Yeah.
So you write what's left on the left, and then it gets compiled somehow, or?
Yeah, there's a compilation step. Yeah.
All right, cool. Thank you so much.
So it's a translation, not a binary instance.
There's both. So what I'm about to look at next is this is a more complex enum. Rust's algebraic type system allows us to use sum types, like the shape that can be either a square or a rectangle with different attributes. Because of this, there isn't really a way to represent this sum type in pure SQL. So with pgrx, we can still use these rich types in the database. In this example, we're casting a single integer, and that gives us a square. And using the JSON style input with like height and width, that creates a rectangle. But they're both of type shape. And so if you had a function that took a type shape in Rust, then it could consume either of those. But this does not get generated. Only the function signature gets generated in SQL. The rest is handled by the binary. So putting it all together, here's a combined example to look at, kind of a typical example of what I work with a typical example of what I do at work. Here, this extension SQL creates a task table when the extension is installed. So this is just like straight up, I want the SQL to run. And this makes it easy to ship kind of schema setup and things like that alongside the code. We can also define a custom enum called status, which maps directly to a Postgres enum using, again, the derived Postgres enum. And this gives us that type-safe usage of the status values across Rust and SQL. And then we have a getTasksByStatus function, which takes a status value and queries the task table for any of the matching rows. We can build the query string and then use the SPI connect block to execute the SQL and then map the results into Rust. And then we can just return it if we want using table iterator, which allows us basically to return a set of rows from Rust to Postgres, just like a table function. And together, this demonstrates how pgrx lets you define types and query data and expose all of that logic in an idiomatic way. So that's how pgrx allows Rust to build generalized Postgres extensions. But how does this apply to the AI extension that I'm building at work, and what problems are we trying to solve? So at EDB, we're not trying to reinvent the AI ecosystem. There's already great tools out there for training and serving models. Instead, what we're building are the shovels and the pickaxes, the tools that make it easier to run AI workloads, again, closer to where the data lives. That means reducing the need for complex ETL pipelines. And so when you can do the inference and the transformation directly in the database, it lowers the barrier for teams to adopt AI. Many of our customers already have tremendous amounts of data in Postgres, and they want to unlock value from that data using AI without migrating it to a separate system. We're also building the infrastructure to support those workloads, from preparing and shaping the data to managing models with an integrated registry that can pull from local storage, the cloud, or even custom sources, and then tying it all together with an in-database pipeline registry so you can orchestrate workflows that might involve batch or kind of live trigger automations. The goal is to empower teams to iterate faster and stay closer to their data, and that way they can adopt AI incrementally without needing a full rewrite of whatever platform they're on. Before models can do anything useful, we have to pre-process the raw data, since most AI models expect input in some specific format, whether that's just clean text or images or something else. Common prep steps include chunking large text into smaller segments to fit within a model's context window. This is especially important for LLMs. If you've ever been talking to ChatGPT and you try to paste in this long file that you're trying to get help with, you might have encountered like a size limit exceeded. That's basically what that is. It can only look at so many chunks at a time. We might also want to extract usable text from unstructured inputs, like using OCR on scanned documents or parsing HTML to clean up the noisy tags and things like that. Even structured files like PDFs often require some cleanup to get clean model-ready text. This is the kind of pre-processing that we're enabling directly in the database, so it can happen right where the data lives. The next challenge is managing the models themselves. We basically wanted a centralized way to store and manage the AI model configurations. Different tasks often need very different models, whether summarization, classification, or embeddings. And each of those unique models that you're using have its own parameters and credentials. So we created something that we call the model registry, and it tracks all of that, all the endpoints, authentication, model types, and tuning configurations. This model registry also ties into Postgres user access controls. So that means that teams can collaborate securely. A data scientist and an application developer can share access to the same model without needing to pass keys around, for example.
Here for model is something like Llama 4 or...
Sorry, what was that?
Here for model is something like Cloud 3.7 or something.
Yeah, or ChatGPT, or yeah. So basically the way it works is there's like a number of model providers, we call them. So that's like OpenAI, or we have a lot of our customers that run servers on-prem. And so there's something that they can deploy called NVIDIA NIM. I forget what it stands for. But it's a model serving framework that can run on your GPUs. And they have a whole catalog of models that you can pick from. The pipeline registry is where we define and manage what workflows we want to run using those models. So we can declaratively define multi-step pipelines that all link together in the database. These pipelines support both batch processing and live trigger-based automation. So we can respond to changes in real time or run scheduled jobs when we need them. Because they run inside Postgres, they benefit from transaction control and consistent access to data, improving both latency and data integrity across the workflow. So let's look at some examples. I just want to, yeah.
So are you seeing that you're creating some store function or force or trigger or something in the backend that will communicate with an external AI engine, send some data to it, get some data back?
Yeah, exactly. Yeah. And sometimes that is external, and sometimes it runs on the server.
The same as a Postgres machine?
Yeah.
Oh, wow.
I just want to clarify, in this context, a pipeline is just a process that takes data from a source, performs some transaction or operation, and then writes it to a destination. And for our extension, a source can be a regular Postgres table or even S3 compatible object storage. And that has been a big value add for our customers who might not have all of their documents, for example, in a table. So here's a simplified version of our pipeline registry schema. At the center is this pipeline registry table, the big one, of course. It holds all of the core information about the pipeline, things like what operation you want it to perform, the output destination, and any of the configuration options. Since we support multiple types of sources, we separate them out into additional tables. Nothing super groundbreaking here, but one of them is for pipelines that pull from native Postgres tables, and the other is for pipelines that read from external volumes. Of course, the separation keeps the core registry flexible, and we can add support for additional sources or additional source types later if we want to. And by modeling the pipelines this way, we can make it easy to manage, track, and orchestrate all of those workflows together.
So what runs the pipelines?
That's a great question. I will come back to that, if you can hold on to that. In this simple example, we're just starting with a plain Postgres table called HTML source, which contains the raw HTML content. And each row has an ID and a content field that holds the HTML string, or the HTML string. And that's this table declaration right here. And then right below that to the right is what the source table of the registry looks like if we create a pipeline. And so the most obvious pipeline, I think, here is one that parses the HTML and extracts the clean text. And the general pipeline registry has an entry like this. Here we see the operation. This isn't super, the content itself isn't super interesting. I think this just conveys the idea and the success that we've had marrying the logic of Rust with storing the state with SQL and in tables. Now I want to look at a more complex example of chaining pipelines together. So let's look at a workflow where we have a PDF that we want to turn into something that a model can understand, specifically those vector embeddings that we talked about earlier. So we start with a PDF file. The next step is to extract the raw text from that PDF. Then the next stage splits that text into smaller chunks. And then we finally generate embeddings for each of those chunks using a model. Each step in this chain is defined as a pipeline. And by tracking them in the registry, we can orchestrate the full process automatically as new data lands. So these are what the tables that store the data for each of those pipelines would look like. Of course, PDFs holds the raw PDFs and the metadata. Parse PDFs stores the extracted text from each PDF. The chunked text table breaks that text into the smaller chunks. And then embeddings contains the vector representations for each chunk. Of course, we have foreign keys linking everything together, making it easy to manage and trace the flow of data through the pipelines.
Quick question on that one.
Yeah.
Are you using PG vector for the vector on the last slide?
Can, yes. Most of the time, that's what our customers choose to do.
So are you uploading the content of PDF somewhere in database, and then you're running it against it? Or
Yeah, so if a use case already has PDFs in a table, this would be the perfect example for that. We also have customers where they have a bunch of PDFs like in an S3 bucket, and they want to consume from that. And so in that case, using a volume source, they can just put in the endpoint for that volume, and we can pull from that.
So
and
then your
take the
pipeline
text.
that runs on the Postgres server is going to pick it up.
Mm-hmm. Yeah.
Is that the content, is that stored as the byte? Is that byte array? How
Yeah, so this, in a lot of our tests, we just like upload the content of the PDF as a byte array.
we fetch it from S3, want to store it again?
No, so this example is assuming you already have the PDFs in a table. If you had the S3 flow, then we wouldn't need to store it in a table also. You would like skip this. You would not have this table. It would just go straight to the text table. Any other questions? These are great questions. All right. And so in terms of what it actually looks like to create the pipelines, that's what this is. We define the operation like parse PDF, and then specify where the data comes from and where we want the results to go. In this case, we're pulling PDF content from the PDFs table and then writing the extracted text to that parse PDF table. To chain the pipelines together, we just need to define the next one to use the output of the previous one. So each stage builds on the last. And again, all of this is declarative. The pipeline registry, the automatic orchestration, and the trigger behavior, all of these are made possible by combining the pgrx features of the custom types, the user-defined functions, and the dynamic SPI functions.
So for each of the operation, you have some Rust code sitting somewhere.
Yeah. Yeah. And I think the way I would describe it is most of the Rust code runs, most of the magic happens when you run this statement, because this is a Rust function that's exposed to Postgres. And what we're doing is we're basically dynamically creating a bunch of like trigger functions, for example. If you want your pipeline to run what we call live automation, then we basically create a trigger on insert, on update, on delete. You want that operation to happen looking at the source table and performing or depositing its result in the destination table. Awesome. I want to talk a little bit about testing and packaging. Testing pgrx extensions is pretty straightforward with the cargo pgrx test command, and that integrates with the standard Rust test tooling. It runs all of the Rust tests in parallel against real Postgres dev instances that you have on your machine. So you can write tests either in Rust or as SQL files, and the pgtest macro even lets you embed inline SQL tests inside Rust code, which is pretty interesting and allows us to use some of the Rust like fuzzing libraries to test SQL functionality, which has been kind of fun. This setup also integrates pretty easily into CI/CD, helping to maintain the quality throughout development. And then, oh yeah, I just wanted to mention that pgrx packages extensions as just standard shared libraries ready to deploy to almost any Postgres environment. Of course, I'm mostly talking about the good things, but there have been a few rough edges. The first that I want to talk about is that the extension update process is not automatic, and it must be updated manually every time, which, as you can imagine, can get pretty annoying during development. We've also run into issues with the test mutexes. Since the tests run in parallel and often involve transactions, if you abort the test process, it can leave behind locks that require you to clean or straight up nuke and rebuild parts of your environment. We've also found that some of the automatically generated bindings, while super convenient, they can be a bit disorganized. So sometimes we clean those up, even though we don't often work with them directly. Finally, pgrx is missing some of the deeper, like more niche APIs for Postgres internals. So let's do a quick, I'm almost out of time. Let's do a quick recap for my lessons learned. I think the biggest win was that bringing AI near the data is really valuable for a lot of our users. Less ETL means faster results, pretty straightforward, but it makes a really big difference in practice. Rust, for us, lived up to the hype on being fast, safe, and expressive. While the ecosystem is young, it has almost everything we need for Postgres extensions. The challenges are pretty real. Rust's learning curve is steep, and we have to build in extra time for onboarding if hires don't know Rust a lot of the time. That being said, we do tend to see a shift in mentality. What starts as annoyance at too much syntax usually morphs into an appreciation for the explicit data models that we can build in Rust. What really impressed us was the modern tooling, and again, from a DX perspective, the standardized LSP, the formatting, the phenomenal compiler feedback, and the integrated testing. These all go a long way to minimizing unnecessary diffs or commits in your repos, and just in general improving the productivity of our team. That being said, Rust is not for everyone or for every project. Not everything needs the level of control or performance that Rust can offer. And other languages tend to be easier for fast iteration, especially for small projects. That's all I got. Any other questions? Yeah?
I saw you can embed C Python in Rust, which means that you can run the untrusted language Python,
Yeah.
making you think it's trusted.
Yeah, yeah. So we did see that, and I think that is really interesting too. Of course, it is technically possible, but it of course goes against the ethos of what we're trying to do. But yeah, I think that's super interesting. Yeah.
So pgrx is a framework for building Postgres extensions in Rust.
Exactly.
And one of the extensions that's out there is PL Rust, which is an extension for writing Postgres user-defined functions. User-defined functions in Rust.
Okay.
But do you have any experience with that? Have you seen that at
No,
all?
I don't. I wish I did.
It was written in pgrx.
Okay.
And by the guy from Zombo.
Yeah.
And he hasn't updated it.
Interesting.
Waiting for.
I wonder if you have any more context.
So I don't. So I will explain something that he knows, but most people don't know. So I'm on the board of directors of PG Central Foundation, which is the host for pgrx. But I've never used pgrx. We took it on to be able to host it from the previous owners and keeping it open source. So no, I don't have any input. But one thing I did notice in what you were saying that I thought needed to be actually clear, because I was looking at the docs today, I was looking at the GitHub today because of this presentation, is that your database encoding must be UTF-8.
Yes.
It does not work with any other encoding. That's a mandatory thing.
Yeah, that's a great clarification. I also, I appreciate you mentioned ZomboDB. I do think those may have been the original creators of pgrx, or what became pgrx. So I wonder if if it hasn't been updated in a while, I wonder if it's some artifact or remnant.
Right, because if I want to write a Postgres user-defined function
Yeah,
in Rust,
yeah,
and have a chance of having it loaded on a cloud database, I need PL. I think I need PL Rust more than anything.
gotcha. Okay.
Well, so first of all, I think that's a positive thing if they only support Unicode.
Yeah.
Please, let's just do that now. It's been a while. No, PL Rust is on RDS. So that's
This is what?
it's on RDS. It definitely it's definitely out there. There are definitely people using it. I don't know about the update thing. But so it's not completely obscure.
No, and if I remember correctly, by RDS having pgrx on it, that allows people to install the PGL.
PL Rust.
Yes. Yes, and so even though the RDS may not have it on there, that they can install it themselves.
No, that's what I'm saying. They do. So
They do have it, yeah.
Yeah. So if
Do you know what version they started? Do they have it all the way back to 13?
I don't know on that. I don't know if they have it all the way back to 13. But if an extension, if you write an extension and you use the PL, if you write it in base Rust, just with pgrx, I think core, you could write. That's fine. You can write it yourself. If you write something that's compatible with PL Rust using the procedural languages, that would be something that could also be portable.
And I imagine
Yeah.
the deployment is simpler in the second case. Because for us, we still need to ship our extension. We're creating a new
Yeah.
extension. We're not creating functions using an extension. If
Yeah.
that makes sense.
Yeah, but it does help too. I think, it's part of the whole idea of open source stuff often is that you have something like pgrx, which is being used by a bunch of different people, and then that kind of helps you split the maintenance, kind of collaborate together on keeping it maintained, keeping it updated, taking care of things. And so it's good to see a lot of adoption of pgrx from many different places. Yeah.
Yeah.
Oh, please go ahead.
Oh, sorry.
Just a question on the Rust.
Yeah.
Can you talk about any concurrency handling that Rust provides?
Yeah, so Rust is really good for concurrency. I love that I can basically write async code for where's the okay, the little microcontroller. I can write async functions and it'll compile down to a fancy state machine without an RTOS or anything like that. There are applications where Rust concurrency is really, really great. Right now, we haven't really explored that side with Postgres. There's some limitations and caveats. There might be some weird stuff with how pgrx handles it, so we haven't gone down that rabbit hole. But in other applications and domains, it's a great story. Yeah.
So I was thinking to use Rust because of its interoperability with all languages. Did you integrate any other language coming from Rust, like C or anything else?
The big one that I did myself was going from, was for Busca, the like file searching library. I wrapped that in Python for my coworkers to use in there. You could just import it like a regular library. And that was, I mean, you have to learn a little bit, of course, but other than that, it was pretty smooth. Yeah. Yeah.
My question was more on the operational side, right? So if you have a system like that, like the pipeline is sure running broad, and I would expect some issues, right? How does this is handled mostly by your customer, right? For instance, if we're doing embedding or if we need to conduct a model, I would expect sometimes throttling or timeouts or whatever like that, right? How is this handled?
Yeah, so we're still learning how to handle some of those more like niche errors, but we do have a I'm trying to think what I can say. We do have like an error handling system so that those errors do get reported, so that hopefully you can get a sense of where they're coming from and how to deal with them. But like the rate limiting is a great example. Like we don't have a built-in rate limiter right now. If you have 1,000 prompts that you want to send to ChatGPT and you get it rate limited, we don't have a automatic like, way
There's
of
no
handling it.
retry, there is not, I mean,
Yeah, we'll retry, but there's no like staggered like retry logic right now.
I have an idea. I did this in Python. I made a small function that sends UDP messages out, so I could actually call this function in my different application triggers and so on, so I could trace what was happening. That might be a good use of doing it in Rust because it's so much faster, so much lighter.
True. That's a great idea.
So I have a question. Like,
Yeah.
now that you spent some time like around the world of being a Postgres extension, like what do you feel like Postgres needs? So in the extensibility area, like there's a bunch of people just kind of working in this space, like building extensions that kind of bolt on to Postgres in one way or another. And over in the recent years, like I feel like in the last 2 or 3 years, there's been a lot of attention there. Like at the Postgres, the big development conference, there was a whole like extra day just devoted to extensions. People kind of talking about this. So it's an area a lot of people are interested in. I'm curious, like just from your experiences, like what do you think could be some of the improvements? Like what would make it a smoother experience, like for extension developers like yourself? Yeah, what are kind of some things that maybe could make Postgres better in the area of like maintaining an extension around it?
That's a great question. I don't know if I have a super satisfying answer, to be honest. Like, I don't think a lot of the issues that we encounter at work are attributable to Postgres.
We had a couple. Like, you had a slide, and like for example, you mentioned upgrades, right? So like having to that one.
Yeah.
So rough edges there.
Yeah, I don't know if this is Postgres.
The internal APIs.
That's
for
true.
sure.
Yeah. But I think
that's kind of PGRX.
Yeah, that's more PGRX. They even talk about it in their README that you were probably looking at earlier. They said it's not a matter of like difficulty; it's just an effort thing. They just haven't done it yet, and so you can like they have a mechanism where you can like, hey, I want this API, and it'll wrap it for you.
Yeah.
But yeah, that's a PGRX thing.
Well, it isn't though, because every PL has to deal with this. Anybody, any procedural language, like as soon as you drop out of C, it's gone.
Yeah.
Right? Like
That's
all
true.
the APIs are gone. So like that is kind of, I feel like an interesting thing that, for example, if those internal API, the more internal APIs are exposed that you can hit through SPI, like boom, like if you can expose something in SPI, every single procedural language out there now has access to it, whether it's Rust, whether it's JavaScript, kind of whatever it is.
Yeah, that's a great point. Like we haven't encountered that a ton ourselves, but that is something that we hear from other teams and other extensions being built.
And that is actually documented on the PGRX front page on the GitHub. Is that's on the to-do list.
Yeah.
It is to work on those internal APIs to add them.
What about crates in PGRX? Do you have issues? You said you use it in trusted mode. Do I remember correctly that they whitelist a set of crates in trusted mode? Or is that PL Rust? Maybe that's PL Rust.
I think that's PL.
Okay. So there's no issues with crates. One other question. Sorry, I just have all the questions coming.
Yeah.
If other people have questions, just jump in. You had an early slide. I'm trying to figure out if you just were kind of glossing over something you didn't say, because you had this little bullet point about Rust and like the sort of the ecosystem of AI-related stuff.
Oh, yeah.
And like Python's super rich, fair, of course. We kind of all expect that because everybody loves Python. Was that like, is that something that was just kind of like a minor the smaller AI ecosystem, is that just like a minor inconvenience, or has this been kind of like something that's, how do you work around that? Is it something you've run into kind of repeatedly a bunch of times that was really kind of just something you've had to live with?
Yeah. Yeah, I mean, like Rust is a new language, but it's like been out for like over a decade. So like we say new language, right? But so our main like areas of friction there is that there's less choice. There's less choice if you want to do a specific kind of model operation. There's like one or two crates, like packages that you can use. And not only that, but there might be limited feature sets for each of those options. And so basically what that has resulted in is us contributing to those dependencies to add some of the more niche features that we might need. It also turned out to be less of an issue than we thought in some respects, because a lot of the model stuff is just like hitting an endpoint. Like it's not super. Again, that's for the cloud stuff. The cloud stuff is relatively straightforward. It's really doing the stuff like locally that can be more challenging. But that's where we've hooked into things like NVIDIA NIM, which is like their framework for running stuff locally, and that has been more straightforward. Yeah, it's interesting because the kinds of like exploratory workloads that you might want to do in Python, like in like a Jupyter notebook, for like exploring the problem space and like trying a bunch of different things out, we found those to be less, like we've still found ways of doing those.
So do you literally have a server with some big CPUs for the Postgres part, and you have several GPU cores in it as well?
Yeah, sometimes. It gets really complicated really fast. We also have like distributed clusters. We have like some people who just want to use the cloud instead. We have a lot of hybrid deployments. But yeah, sometimes we'll have it all in one box.
So what kind of models do you numbers of parameters that you usually need to use? Like 13 billion, 70 billion, or how big do you go?
Yeah, the classic question. It totally depends. And like, it's the worst answer. But, yeah, depending on what you're trying to do, if you're just trying to like classify images, like see if there's a dog in an image, right? Versus like, if you want like an LLM type response.
I was thinking about your summaries where you're trying to rank up the reviews, for example.
Yeah.
What kind of AI do you need for that?
Yeah, so there's actually different models. So in, I think you were talking about, no, it was way back here, the workloads. This one. So each of these, this is actually like a compound pipeline, right? Because these are all different steps. So they might use different models. Yeah, so you might have different models to do different things.
Some for extracting the keywords and some for comparing.
Exactly. Like there are models that are designed to extract text from PDFs. Like that's what I was working on the other month. And so you probably wouldn't ask that model to tell you the best spots in Seattle for sushi or something, right?
Other questions? I have one last question. You guys all go first.
Can you go back to this slide where we show the function, the substring function?
The substring function, yeah. Here we go.
What is happening here?
So my understanding is that this bundles my understanding is that this compiles this down to a binary, and then it writes the pgrx is writing the function signature to call into that binary.
Say binary, you mean basically a shared object, like a library file.
Yeah, a library file. Yeah.
And then if I want to be more specific, like, because I see input being a string.
Yeah.
Does this means, maybe it's more too much specific, that the actual memory of the input text is copied over? Do you know how the memories are located in cases like this? Because I can tell you that the input to the Rust function owns the memory.
Right. Yeah. So whether it takes a copy or if it moves it.
If it's external, it should be copied.
Yeah, I would think that it would be copied. I'm not sure. I'm not.
Why are you using copy?
It's going to be a question of how pgrx does it under the hood. You don't have any control over it at the level you're working at, right?
Well, I know this does work. I do happen to know. So this this slide originally started as a string slice, like the ampersand str, for those who are familiar. But I changed it because I thought it was maybe a little too confusing. But it still works. But the function signature is the same. The SQL function signature is the same. It still asks for text. So it must be doing something different under the hood.
Isn't it just a convenience for using a foreign function interface?
Probably.
I think so. Yeah.
Yeah, but my question was if that string is possible or just a reference. Because in Rust I can tell you this string is not going to change, right? So I don't need to copy over it.
Yeah, that's why I think it has to copy.
Okay.
Because you can ask for the string slice, so I think you would get a reference.
I would imagine the input is probably by reference, but I suspect that it's making a copy on the way out, right? Because from SQL's perspective, the input and the output string are going to be separate. I don't know PG internals well enough to know whether or not that's a feasible option to say these two different text strings, this is a slice of that, right? I don't know whether PG has
It
that.
has to be because it's usually zero terminated. So if it was the original one, it would not write a zero in the middle.
Right. That's right. Yeah.
That's not how Rust works. I can tell you.
No, that's not how Rust works, but I'm saying I think that's how PG works.
Okay, but I can tell you that if you write that in Rust.
Oh yeah, no. Oh, I'm saying that from the interop perspective, I'll bet you it's making a copy on the way out, but it may not be making a copy on the way in.
Okay.
So,
Yeah.
do you see some of your customers using pgrx framework for like agentic deployment?
For what? Sorry.
Agentic deployment.
Not really. At least not that I've heard of. Well, that's really interesting.
Given the like talk about like, the fine grained of control that you have with it, maybe for agents that are running tasks like really close to the database, maybe.
Yeah. I think that's the goal. I don't know of any that are, like, I'm not super customer facing, so I totally am not like in the loop on every single thing that happens. But I think that's what a lot of the use cases are driving towards. That's a big,
Like you see them wanting to do that.
yeah.
Jeremy?
Or anything else? Because I just have kind of a totally different direction random question. Yeah. I want to know about your t-shirt.
My t-shirt, yeah. So we had a work event here like almost exactly a year ago, right after I joined in Seattle to workshop kind of what our AI extension was going to look like. And I guess we had t-shirts made,
Nice.
and then we had a summit in London, and that's when I got the t-shirt.
Because
We got the t-shirts made
after
after.
like EnterpriseDB logo, and it's like a Seattle
Yeah,
skyline.
it was the Stacy
How
Nolan.
fitting.
How big is the team that built this? This sounds like a pretty big.
Yeah, so we just hired, but for most of the time, well, the tech preview was built like by 2 or 3 people, the first iteration in Python. But this newest iteration has been, like, I would say like 4 core engineers and like 2 like AI expert consultants kind of on the team, but not actually writing the code. Yeah. It's been super fun. I love building stuff from scratch.
Are you hiring more people?
Maybe?
Good answer. Yeah.
Any other questions?